Hello dear students, welcome to the channel and very warm welcome to this playlist in which we are discussing about 8085 microprocessor. Up until now we have seen so many different things. We have seen how do we define memory address, how the registers work, how do the memory works in 8085. We have seen different type of registers and different type of uh, different ways how we can store memory in 8085. We have seen pin diagram, we have seen architecture, and today we are going to discuss the timing diagram of 8085. Now you might have a question, what is it? So in order to understand every instruction in a better manner, it's essential to understand the microprocessor executes. How does the microprocessor executes these instructions, and which signals are activated in order to execute particular instruction, right or not? So which signal acts as a timing reference, and what is the duration of each signal for particular operation? So the timing diagram is the diagram that answers all these questions, right? We draw a graphical representation of steps with respect to time, including clock, right? And this graphical representation is called the timing diagram. Now it includes three cycles: instruction, machine, and t-state. I will explain all of them one by one. First, coming to instruction cycle. So CPU fetches one instruction from memory at a time and it executes it. So the essential step required the CPU to fetch and execute an instruction is called the instruction cycle, right? And instruction cycle consists of fetch cycle and execute cycle. So when you combine fetch cycle with execution cycle, you will get instruction cycle. So in fetch cycle, the CPU fetches an opcode of the instruction from the memory, and the steps required to acquire the data from the memory and complete the operation which is specified in the instruction is constituted by the execute cycle, right? So you just have to add the fetch cycle and execution cycle, and you will get instruction cycle. Then we have the machine cycle, right? And all these cycles, by the way, all these cycles are carried out in synchronization of clock, right? All these cycles are carried out in synchronization with the clock. Then we have the machine cycle. So the time which is required by microprocessor to complete the operation of accessing memory, or you can include the input output devices. So that cycle is called the machine cycle, right? Which is the time required by my processor to uh, to complete the whole operation of accessment of this memory or input output devices, right? So which operations does this perform? It performs operations like opcode fetch, memory read, memory write, IO write. We are going to learn about them in detail now in this lecture only. So the instruction cycle consists of several machine cycles, right? And time the timing diagram which we are going to draw would be the machine cycle itself for today, right? So there can be different type of machine cycles. For 8085 we have 7 different type of machine cycles that generally generated at the beginning of each machine cycle, and the remaining remains valid for duration of this whole cycle, right? So which cycles we have, I'm going to discuss that as well, but before that let's discuss t state. So microprocessor performs operation in specific time period, right? Specific clock cycles, and every single clock cycle is called t state. So number of t states required to perform an operation is the machine cycle, right? So machine cycle consists normally 3 to 6 stages, and one t state is a one clock period. So an instruction cycle consists of 1 to 5 machine cycle total. Do you understand? T state smallest, several t states. When you combine several t states you get machine cycle. When you combine several machine cycles you get instruction cycles, right? So number of t states required to perform operation, machine cycle, and number of machine cycles required to perform instruction cycle is around 1 to 5 machine cycles. Then representation of signals in timing diagram. How many different type of signals do we have? So first we have the clock. So it pins x1 and x2 pins which provide clock generator, and this frequency is divided by 2 and used by the microprocessor, that we learned when we were discussing about the architecture. By the way, if you want to learn more about the architecture and pin diagram, the link will be flashing on the I button on the top right hand side corner of your screen. You can click on it and you can find it very easily over there. So waste no time and you can check out and then come back to this video very quickly. Now moving forward, ideal clock should be exact, having very less rise and fall time, right? But particular clock is different. It consists some rise time and some fall time, and that you will be seeing. Let me show you. This is the clock signal. See, there is a fall time, there is some fall time, then it remains stable, then we get some rise time. So it's not totally steep, it's steep but it's not upfront, right? Because this is not an ideal clock cycle, this is practical clock cycle, and microprocessor is a practical device. Then we have the single line signal. So status of a single line can either be low or high, simple enough, and hence any one state logic 0 or 1 will be executed. But the change for one state to another is not possible in zero time, it takes some time, and because of that you will see the slope here as well. See, let's see this IOM cycle or ALE cycle, they have the single line signal, right? So see, it takes some time to go from 1 to 0. So the 1 is the high value, the 0 is the low value. So see, in ALE it takes some time to go to 0 to 1, then again some time to move from 1 to 0. So it does take some time. Then we have the multiple line signals. Let's come back here. See, multiple line signals. So processor have multiple lines, and signals can be called as a bus signal. Instead of showing each line using single line signal, they are grouped together and shown in form of the block. So see this one, status signal of R, or S0 S1 signal you can also call. This is a multiple line signal. As you can see here, see, we have multiple lines. So S0 and S1 have shown in multiple lines. So you can see this crossing over here, there is a crossing. So at the time that signal changes takes place, and for the rest of the time the content of these lines are valid and you can use those signals. And if lines single line change occurs, then we have to show crossing to indicate the change in the content. As okay, so even if S0 changes and S1 remains as it is, you have to show the crossing, right? Then we have the multiple lines with higher impedance that we have not covered in this today's cycle. We will be learning about it in detail in the upcoming time. Then we have single line single effect cycle. So because of the straight line of other signals will also change, the change in the one line signal takes place, and it causes the change in the other signals as well, right? So on the change of one state of particular line, the other line will also vary its signal. So see, as the IO machine cycle is changing, we are seeing change in the write cycle as well. See, so that is single line single effect signal. Then we have the multiple line single effect signal, when change in multiple lines causes change in a single line. So we don't have the example of it in today's class, but we will see that in upcoming classes as well. Then we have something called, okay, sorry, yeah, this is the list. We have seen up till here. And before we move to ALE, let me show you the A to A15 higher order address. This PCH is showing A to A15 higher order address, which is available on A to A15 bus. And during T1, T2 and T3 state, you can see it's taking place. In T4 it's switching itself, and during T4, T5, T6 the opcode fetch contains nothing. That's why it's unspecified, right? There is no content in that in those buses during T4, T5, T5, T6 clock, T6, T states. There is no content over there. Similarly, we have the lower order address. Always remember, where do the higher order address, which register points the higher order address? H. And which register points the lower order address? L. And this PC stands for program counter. So always remember, program counter, which is indicating the memory location that is pointed by the register H, and the program counter indicating the memory location pointed by the register L, right? So lower order address uh, is limited to the first T state only, which goes from 80 to 87, and it operates in the first it carries the address during the first machine cycle only. After that, during memory read operation, we can see four memory read or IO devices is transferred to 80 to 87 lines, and during AND states, right? So it operates differently based on the requirement of machine cycle in the T2 and T3 states. But generally in opcode fetch cycle it contains opcode. If you move to memory write cycle, let me show you. The one in the right is the memory write cycle. So you can see in memory write cycle what is happening, right? So during memory write cycle, the data from microprocessor is transferred on 80 to 87, right? So data is transferred on 80 to 87 lines as soon as the address 80 to 87 is removed. See, it contains lower order address during that time. Then let's move back to ALE. Here ALE status and read write control. Three signals are remaining. See, this is ALE, which stands for, of course, address latch enable. This signal is available during the T1 state only. In every single machine cycle you will find ALE, and it will be available during the T1 state only in every single machine cycle, right? So it's basically a pulse signal which is used to latch the address from 80 to 87, and then the ALE signal with respect to clock signal is visible here. See, it will always be opposite of the clock signal, and it will be only activate for one pulse or the first T state in every single cycle. You can see here, see ALE, just this here, here as well. Everywhere you will find ALE activated for the first T state only. Then we have the status signals. We have discussed about it earlier, so I'm not discussing in detail. Then we have the control signals, which are decided signals that decide the operation to be performed, like for memory read, opcode fetch, input output read, and RD signal is activated during T2 T3 state of machine cycle. For memory write, IO write and write signal is activated during T2 and T3 state of machine cycle. That you can see. Let me show you. See, sorry, let's move to memory read and memory write. See, during memory read is activated during T2 and T3, and during memory write WR is activated. Same will be visible during IO read and IO write. See, this is IO read on the left side and this is IO write on the right side, and the other one will go opposite to uh, IO/M instruction, right? So what are the machine cycles and their timings in 8085 machine cycles? First one is the opcode fetch cycle. So the microprocessor uses this cycle to take the opcode of an instruction. You can also call it fetching of opcode for opcode. And in this case, the address of the memory location where the opcode is stored is given by the program counter. So you can see here it's given by the program counter. See, PCH and PCL, right? So this is always the first cycle of any instruction cycle. So if you are whatever instruction cycle you are going for, the opcode fetch cycle will always be first, and you have to draw it. So this is most important fetch cycle among every single cycle. So the opcode is taken from memory and transferred to instruction register for decoding and execution. And how many states it requires? As you can see, it requires around 4 t states, because after 4th t state there is no change taking place over here. See, there is no change. T5 and T6 is just repetition of clock signal. Unspecified remains as it is. Nothing is happening in 80 to 87 state. ALE is remaining as it is. IO machine remaining as it is. Read and write and status, everything is remaining as it is. So around 4 stages. But if you are uh, if you want to draw 6, you can draw 6 as well. Then we have the operand fetch cycle. Operand fetch cycle is a cycle that takes 2 to 3 byte instructions. But in 2 to 3 byte instruction, taking opcode doesn't complete the instruction fetching, does it? So we required the operand fetch cycle. For 2 byte instruction, we required 1 operand fetch cycle, and for 3 byte instruction, we required 2 operand fetch cycles. And in this cycle, the address is given by the program counter again, right? So again, address is given by program counter, similar to opcode fetch cycle, but the contents are not transferred to instruction register. Instead, they are stored in the temporary register, and the time required to complete the operand fetch cycle will always be 3 t states. As you can see here, it is limited to 3 t states only. Then we have the machine memory read cycle. So processor executes these cycles to read data from memory, simple enough, and address of the memory location is given by instruction. So the program counter is not used here, and instead the instruction will be given instruction will give some address, or will specify where the address is present, right? And during this memory read and upcoming memory write cycle, the IO memory will always be 0, right? We saw the table in the previous class, if you remember. So microprocessor executes memory read and memory write, both cycles. So memory write is similar to memory read. It's just that processor is executing these cycles to write data to memory instead of read, and address to memory is given by again same instructions, IO memory 0. Then we have the IO read and IO write cycles. Again, we execute these cycles to read data from IO devices, or to write data, or to send data in IO devices. So the because we are using the IO devices, the status of the IO line will be high, and the address. Then we have the interrupt acknowledge cycle. So in response to interrupt request input, the microprocessor executes this cycle to read the information for interrupting the device. Then we have the idle machine cycle. So the microprocessor executes this cycle for internal execution, and during this cycle all data address and control lines are tri-stated, so the microprocessor does not perform any external operation. So in 8085 there are different instructions which doesn't complete execution in given time period, and these instructions are required idle machine cycles to complete the execution of the instruction. Right, now we are going to see every machine cycle in detail. Now let's discuss the opcode fetch cycle. So 8085 uses this cycle to fetch the instruction opcode from memory, and in this case the address of the memory is always given by the program counter. So the program counter is incremented by 1 point to the next location. There are two types of opcode fetch cycles, one using 40 states and to complete the operation, and other using 60 states for completion of operation. Generally 40 states is more convenient and easy to use and draw, so we use 40 state one. So let's see the first stage. In the first stage 8085 sends the status signal. So you can see this T1, the IOM is activated at 1, and in this what happens, the S0's value will remain 1 and S1's value uh, my apologies, the IOM and S0 will be activated, the status signal IOM. So these two and these total three signals will be activated. First, IOM will become 0. Initially it is 1, it will become 0 in the first t states. S0 will become 1 and S1 will become, sorry, S0 and S1 both will become 1. Apologies, S0 and S1 both will become 1, and I0M will go from 1 to 0. Okay. So 8085 will send 16-bit address on A8 to A15 and 80 to 87. The higher order byte of program counter is placed on the A8 to A15 lines, and it remains there up to T3 states. The lower order byte of program counter is placed in 88 to 87, as you can see, which will remain only for T1 state, as we discussed. During this state, the address latch enable or ALE will give positive pulse, which represents the contents of 80 to 87 as an address, and ALE signal is used to latch the address to A0 to A7. Here no control signal is generated. Step 2, what will happen in T2 step, T2 state. So the content of program counter, especially the lower order address, will disappear, right? And on A0 to A7 lines, the same lines will be used as a data lines now. So content of A0 to A7 are still available for memory from external latch, but now control signal read will be made low. As you can see here, read is made low by the processor, which will enable the read circuit to address the memory device. So the memory device then sends the content on the data bus, right, where 80 to 87. And in addition to that, the processor will increment the program counter content by 1. It will happen every single time, and I will not repeat that same thing, but it will happen in every T state. So then we have the T3 step, T3 state. During this again clock cycle, during this clock cycle, the data from memory like opcode is transferred to instruction register RD control signal will be made high, and then the then RD will disable the memory device. Simple. And this is the only thing that is taking place right now. During T4, the microprocessor will perform only internal operation. The opcode is decoded by the CPU, and upon decoding 8085 knows all the information, like whether it should enter the enter into T5 and T6 stages or not, and how many byte of instruction is it, right? So if the instruction doesn't require T5 and T state, it will not go there, and if it is required, then multi-byte instruction, in the case of the multi-byte instruction, the operand fetch cycle are executed to complete the instruction fetching. And if we go from T5 to T6 stages, what will happen? The uh, whatever thing is remaining to complete the decoding and some operations are inside the 8085 will take place, right? And the operation will strictly based on whatever instruction given to it. Then we have the operand fetch cycle. I'm going a little bit quick because we we don't have the time luxury over here. This 8085 operand fetch cycle is used to fetch the operand of an instruction if it is multi-byte instruction in order to read the data from the memory. So the difference between two is, operand fetch, the address of the memory location is given by the program counter, and in memory read the address is given by the instruction. So these operations require the three T stages, T1 to T3. In first step, the T1 state, the 8085 will send appropriate status signals, which means IO slash M will become 0. It is C, initially it is 1, it's becoming 0. S0 will become 0 and S1 will become 1. The 16-bit address is transferred to 80 to 87. See, 80 to 87. Lower order will be 80 to 87 and higher order will be 8 to A15. Right. Then the address, once address is given, then program counter is incremented by 1, and in memory read cycle the address depends upon the instruction. So address may be from stack pointer or it can come from general purpose register as well, right? And if it comes from general purpose register, always remember it comes from HL pair. Then ALE will be using ALE will generate address latch enable is generated by 8085 to indicate the availability of address A0 to A7 and A0 to A8 to A15. So the ALE is used to latch A0 to A7. In the second step, what will happen? In T2 state, the lines 80 to 87 will be used as D0 D7 to transfer data, and the control signal read is made low. As you can see here, control signal is made low, which will enable this selected memory, and the memory will be send the data on the data bus. In the third state, what will happen? Data from the memory will be transferred to 8085, and 8085 will accept this data and will transfer to whatever the internal data bus exists, and then read will made high. After that, read will made high. So remaining process will be same as opcode fetch, except there is no further stages after T3. So generally it's stored in a general purpose register. If the operand fetch cycle, if it's the operand fetch cycle, then it is loaded in temporary register for further use. So operand fetch cycle, the program counter contents are incremented by 1 and to the points to the next location. Then we have the memory read, memory write. Let's see memory write first. So memory write is used to store data in either data memory or stack memory. And if it is a data memory, then address will be generated by general purpose register pair, HL register, always remember. And if it is stack memory, then address will be generated by stack pointer. Again, memory write cycle requires 3 stages, uh, T1, T2, T3 stages, and T1 state will be the same as opcode fetch and operand fetch, except the value of IOM and S0 S1 will be changing. So IOM will be still going from 1 to 0, but the value of S0 will become 1 and S1 will become 0. Other things will remain as it is. In the second step T2 step or T2 stage, the address of 80 to 87 will be removed. So address on 80 to 87, like A0 to A7, is removed, and the data to be stored in the memory is transferred on these lines. So the control signal write is made low. See here, control signal is made low, and the write uh, This low will make memory activate to accept the content on the data bus, right? It will make accept the content on the data bus, and the accepted contents are stored in the selected location. Sorry, we changed the slide. T3 state, the in the T3 state, the data from the data bus is stored in memory location WR is made high, which deactivates the memory and microprocessor completes the machine cycle. Now at this stage we have built basic platform for drawing timing diagram for particular instruction. So now you can draw this read cycle from memory write cycle. See, there is no change in other things except we are interchanging memory read and memory write cycle. See, because in memory read cycle what do we have to do? We have to read the data from the memory. In memory write we have to write the data in the memory. So we used to activate write cycle here, or a write instruction here, write signal here. But in read what do we have to do? We have to read the data from the memory. So we will be activating read signal during the T2 state instead of activating write signal during T3 state. So that is the only change, except everything will remain as it is. That one thing, and except that there is one more thing. S0 will become 0 and S1 will become 1. So these two will interchange their positions, or will remain complementary. S0 will become 1 and S1 will become 0, right? So that would be the change. I'm not going into the detail of memory read at this particular point in time, because time is limited and I have to discuss IO read and IO write today. So these machine cycles are similar in the memory read and memory write machine cycles, but in these machine cycles the IOM signal is high for IO read and IO write machine cycle. So see, it is going from 1 to 0. 1 to 0. See what was happening earlier, right? It is going 1 to 0. But these machine cycles, the IOM signal is high for input output read and input output write machine cycles, right? And except that other things are remaining as it is. If it is a input write, then the write will be activated, will go low during S0, and S1 and S0 will be same as the memory write. So see, S0 is 1, S1 is 0. It's remaining same as memory write. Only thing, this IO address will be activated in in the address bus and data buses. Other things are remaining as it is, right? See, IOM is also remaining as it is. It's going from 0 to sorry, 1 to 0 again, 1 to 0, 1 to 0, right? So that's the that these are different timing diagrams we learned today. So if you have any doubts, any queries, please mention them in the comment section below. I will be seeing you next time. Till then, thank you very much for listening. Goodbye for now.